Okay, let's unpack the whole idea of time travel. I mean, it's everywhere in our stories, right?
Yeah.
Films, books, you name it.
It absolutely is. But what happens when we, step back from the fiction and ask what actual science says? Is it even possible?
Yeah. What's the real story? That's what we're diving into today.
And surprisingly, there are some serious scientific theories grounded in physics that suggest it might not be purely fiction. We're talking relativity, quantum mechanics, some really fascinating stuff.
Fascinating and frankly mind-bending. You start thinking about paradoxes, changing the past. It can make your head spin.
Definitely.
And for you listening, if you want to get the essentials without getting totally lost in complex equations, that's our goal here, a shortcut to the key ideas.
Exactly. So maybe we should start with Einstein. His theory of special relativity really shook things up.
Right. The big insight there was space-time, that space and time are connected.
Precisely. Not separate things, but woven together. One fabric, space-time.
Which means time isn't like this universal clock just ticking away the same for everyone.
Correct. Special relativity showed that time is relative. It actually depends on how fast you're moving.
So the faster you go, time slows down for you, compared to someone standing still.
That's the essence of it, yeah.
Okay, maybe an analogy helps. Like imagine time is a river. If you're zooming down that river in a speedboat, your watch on the boat would tick just a tiny bit slower than a watch sitting on the riverbank. Is that kind of right?
That's a great way to think about it, actually. And it's not just theoretical.
Ooh, we've seen this.
We have. Astronaut Scott Kelly, spent nearly a year on the International Space Station, moving very fast.
Right, orbiting Earth.
When he came back, he'd aged just slightly less than his twin brother, Mark, who stayed on Earth. About 5 milliseconds less.
Wow, okay, that's tiny, but it's real. He literally time traveled just a fraction into the future.
In a manner of speaking, yes. That's time dilation due to speed.
Okay, so speed affects time. What about gravity? Does that play a role too?
It absolutely does.
Yes.
That's where Einstein's general theory of relativity comes in. It tells us gravity also warps space-time.
Warps it, like bends it.
Exactly. Think of putting a heavy bowling ball on a trampoline.
Okay, yeah, it makes a dip, a curve in the fabric.
That's essentially what massive objects like planets and stars do to space-time. They create these gravity wells.
And does that affect time too? Being in one of those wells?
Yes. The stronger the gravity, the deeper you are in the well, the slower time passes.
So a clock near the Earth's core would tick slower than one on a mountaintop.
Fractionally slower, yes. And much slower than a clock on a satellite way up in orbit where gravity is weaker.
Is that measurable, like the
Okay.
Scott Kelly thing?
Oh, definitely. It's crucial for things like GPS. Those satellites are moving fast and they're in weaker gravity. Both effects change how their clocks tick compared to ours on the ground. Engineers have to constantly adjust satellite clocks. If they didn't account for relativity, your GPS location would drift off by miles every single day.
That's incredible. It's not just theory, it's practical engineering. Okay, my mind is kind of blown already.
It's pretty profound stuff.
So moving fast, or being near strong gravity, it pushes you slightly into the future. What about the famous twin paradox? How does that fit?
Right, the twin paradox. It's a classic thought experiment stemming from this. Imagine one twin stays on Earth. The other takes a long, super fast spaceship journey.
Okay.
When the traveling twin returns, relativity predicts they will have aged less than the stay-at-home twin.
Because time moves slower for the one zipping through space.
Exactly. Though at any speeds we can currently achieve, the difference would be, pretty negligible.
But theoretically, a really fast ship or maybe hanging out near a black hole, that is a form of time travel, just one way, into the future.
That's a fair way to put it, yes.
Yeah.
You're moving forward in time just at a different rate than someone else.
But going faster than light to reverse time, that's still a no-go in normal space.
As far as we understand physics, yes. Speed of light is the limit.
Yeah.
But speaking of black holes, the movie Interstellar actually did a pretty decent job showing extreme time dilation. Remember that planet near the black hole?
Oh, yeah. Where 1 hour for them was 7 years back on Earth.
Precisely. That kind of massive gravitational time stretching is what general relativity predicts near something as dense as a supermassive black hole.
Okay, so future travel seems possible, if difficult. But the real sci-fi dream is going back, right? What about things like wormholes?
Ah, wormholes. Now we're getting into even more speculative territory, but still rooted in relativity.
They're like tunnels through space-time.
That's the idea. Imagine space-time as a sheet of paper. You could travel the long way across it, or...
Or you could fold the paper and poke a hole through, connecting two distant points. A shortcut.
Exactly, that's the wormhole concept. A theoretical tunnel connecting potentially vast distances in space.
Could they connect different times, too? Not just places?
Theoretically, yes. That's where it gets really interesting for time travel. A wormhole could, in principle, link one point in space-time to another point in the past or future.
Right.
Or maybe even, some speculate, different universes.
Whoa, okay, hold on. Different universes. And traveling to, say, the 1800s. This sounds amazing, but what's the catch? You said theoretical.
Big catches. First, we've never actually seen one. There's solutions to Einstein's equations, but no observational evidence yet.
Okay.
And second, to keep a wormhole stable and, traversable so you could actually go through it, you'd probably need something called exotic matter.
Exotic matter, what's that? Sounds weird.
It is weird. It's hypothetical stuff that would have negative energy density. Normal matter has positive energy, creates attractive gravity. This stuff would need to have, well, repulsive gravity, essentially.
Negative gravity.
To prop the tunnel open?
Sort of.
Yeah.
To counteract the tendency of the wormhole's throat to pinch off and collapse instantly. Without something like this exotic matter, it likely wouldn't stay open long enough for anything to pass through. So we need this magical anti-gravity stuff that we don't even know exists.
Pretty much. Kip Thorne, the physicist who consulted on Interstellar, did a lot of work on this. He showed that if you had stable, traversable wormholes, potentially held open by exotic matter, you could theoretically use them for time travel.
Yeah.
Like step in one end in 2025, step out the other in 1800.
Mind-boggling. But didn't Stephen Hawking have doubts about this?
He did. Hawking described wormholes as potential shortcuts, yes, but likely incredibly unstable and governed by physics we don't fully understand yet. He was skeptical they could be large enough or last long enough for macroscopic travel, especially time travel.
And yet, in sci-fi, Doctor Who, Star Trek, they just pop through wormholes like it's catching a bus.
Right, they're very useful plot devices. Real-world scientists are actually looking, though, using things like gravitational wave detectors to search for signs of maybe tiny, fleeting, naturally occurring wormholes.
Tiny ones, not exactly spaceships going through.
No, not at all. So wormholes are theoretically fascinating, maybe possible according to the math, but require things like stable negative energy that we just don't have. They seem inherently unstable.
Okay, wormholes are a long shot. What else does physics offer? I think I heard something about spinning cylinders. Creating time loops.
Yes, now you're talking about closed time-like curves. Another strange possibility allowed by general relativity.
Closed time-like curves, so paths that loop back on themselves in time.
Essentially, yes. Paths through space-time that could theoretically bring you back to your starting point, not just in space, but also in time.
A time loop. That sounds problematic. Paradoxes galore.
It definitely raises those questions. The most famous idea here is from Frank Tipler. He proposed that a very, very long, incredibly dense cylinder spinning extremely rapidly.
How dense? How fast?
We're talking like maybe 100 kilometers long. The mass of the sun spinning close to the speed of light.
Okay. Wow.
He theorized that such an object would drag space-time around with it so intensely that it could create these closed time-like curves nearby.
So if you flew your spaceship around this monster cylinder in the right way, you could follow a path back into your own past.
That was the theoretical suggestion. A spaceship navigating these loops could potentially travel backward in time.
Building something like that sounds completely impossible.
Astronomically difficult, yes. Maybe fundamentally impossible. And later analysis suggested it might need to be infinitely long or, again, rely on that negative energy we talked about.
An infinite cylinder.
Right.
Easy peasy.
Not quite. There are other theoretical concepts, too, like cosmic strings.
Cosmic strings, like defects in space-time.
Hypothetical leftovers from the early universe. Super dense, one-dimensional things. The idea is maybe if two of these flew past each other very fast, their combined gravity could warp space-time enough to create time loops.
But again, hypothetical strings, extreme conditions.
Exactly. All these general relativity scenarios, Tipler cylinders, cosmic strings, even traversable wormholes, seem to require conditions or materials that are either purely theoretical or likely physically impossible, according to our current understanding. Infinite structures, negative energy.
So the math allows it on paper, maybe, but reality puts up roadblocks.
That seems to be the case. Kip Thorne and others actually showed back in the 70s that mathematically time machines weren't ruled out by general relativity. But there's a strong feeling, a suspicion among physicists that nature probably prevents them.
Like Stephen Hawking's idea, the chronology protection.
Precisely. Hawking proposed the chronology protection conjecture, basically arguing that the laws of physics themselves likely conspire to prevent travel into the past, precisely to avoid the paradoxes it would create.
Ah, the paradoxes. We keep bumping into them. Okay, before we tackle those head on, what about the other side of physics, quantum mechanics? Does that offer any loopholes?
Good question. Quantum mechanics, dealing with the very small, the subatomic world, definitely has its own share of weirdness that touches on time and reality.
Yeah, particles being in two places at once, spooky action at a distance, all that. How does it relate to time travel?
Well, one very provocative idea is the many worlds interpretation.
Many worlds, you mean parallel universes?
Sort of. The idea is that every time a quantum event happens where there's more than one possible outcome, like an electron could spin up or spin down, the universe doesn't just pick one. It actually splits. A new branch of reality is created for each possible outcome.
So one universe where it spins up, another identical one where it spins down, and this happens constantly.
That's the core concept, yes. An ever-branching tree of parallel realities constantly splitting off with every quantum choice point.
Okay. That's a lot of universes. How does this help with time travel paradoxes?
Well, think about the classic grandfather paradox. You go back, prevent your grandparents from meeting, so you're never born. Paradox.
Yeah, big one.
In many worlds, the theory goes, when you travel back and change something, you don't actually alter your original timeline. You just shunt yourself onto a new branch.
So you create a new parallel universe where your grandparents didn't meet, and that universe's version of you is never born.
Exactly. But your original universe, the one you left, continues on unchanged. You haven't paradoxically erased yourself from your own past.
Yeah.
You've just entered or created a different past in a different universe.
So it resolves the paradox by saying you can't change your past, only create a new alternate one.
That's the potential resolution it offers. But, and this is a huge but,
There's always a but.
even if many worlds is correct and these parallel universes exist, we have absolutely no known physical mechanism for traveling between them.
Ah. So infinite universes might exist, but they're all, like, locked off from each other. We can't just hop between timelines.
Precisely. Each branch, once split, evolves independently according to the laws of physics. There's no known way to cross over. Same goes for other multiverse ideas, like bubble universes from cosmic inflation. They don't seem to offer a route for backward time travel within our own universe's history.
Okay. So many worlds is maybe a philosophical fix for paradoxes, but not a practical method for time travel. What about entanglement? The spooky action at a distance. Seems like instantaneous connection. Could that be used?
Entanglement is genuinely bizarre. Two particles linked no matter how far apart. Measure one, and you instantly know the state of the other.
Faster than light, right? Could you send a message back in time that way?
It looks faster than light, but crucially, you can't use it to send controllable information faster than light. You can't force one particle into a specific state to send a deliberate message to the other one instantly. The correlation is there, but it's random, probabilistic, no signaling.
So no FTL messages, no sending information to the past via entanglement.
Correct. Although, interestingly, there are some theoretical connections being explored between entanglement, black holes, and maybe tiny quantum wormholes. ERGO bridges, they're sometimes called.
Entangled black holes connected by many wormholes. Seriously?
Highly theoretical. But even that doesn't seem to offer a path for, people traveling through time. So quantum mechanics adds layers of weirdness and maybe philosophical solutions, but not a time machine blueprint.
Okay, back to the big problems then. The paradoxes. The grandfather paradox feels like the showstopper.
It really is the classic illustration of the logical problem. You go back, prevent your own existence. It creates an unavoidable contradiction. As physicist Paul Sutter said, if you change the past, you change the present, but the present already exists. It just doesn't compute logically.
It's self-canceling. If you succeed, you wouldn't have been there to succeed.
Exactly. Then there's the bootstrap paradox or ontological paradox. It's slightly different. It's not about preventing existence, but about origins, where something, an object, information has no clear starting point because it's caught in a time loop.
Ah, like the story of the time traveler giving Shakespeare a copy of Hamlet. Shakespeare copies it, becomes famous. But who actually wrote it?
Precisely. The information, the play itself, seems to come from nowhere. It just exists within the loop. Philosopher Tim Maudlin called these things self-caused. The information exists because, well, it exists in the loop.
Like pulling yourself up by your own bootstraps, hence the name.
That's the origin of the term, yeah. You see this in fiction a lot, too. Terminator, with the technology from the future enabling its own creation.
Or predestination, which is almost entirely built around a mind-bending bootstrap loop involving a person's own ancestry.
Absolutely. These loops aren't strictly logically impossible, like the grandfather paradox often seems to be. They can be self-consistent, but they raise really deep questions about where things actually originate. Where does the information or the object first come from if its existence relies on its future self being sent back?
It feels like the universe just shouldn't allow these things.
Many physicists agree. Which brings us back to ideas like the Novichok self-consistency principle.
Right, you mentioned that. The idea that the timeline sort of protects itself.
Kind of. It suggests that if past time travel were possible, the laws of physics would somehow ensure that any actions taken by the traveler were already part of history. You couldn't actually change anything in a way that creates a paradox.
So if I went back to stop my grandparents' meeting, I'd fail. My attempt would somehow be the reason they did meet, or I'd just be prevented. The outcome my birth is fixed.
That's the gist of Novikov's principle. Any attempt to create a paradox would be intrinsically impossible or would unfold in a way that preserves consistency. History is robust.
And Hawking's chronology protection is like a more fundamental version. Physics itself forbids the loops.
Yes, Hawking suggested the very formation of these closed time-like curves might be physically forbidden, nipping paradoxes in the bud before they can even start.
So the consensus seems to lean pretty heavily against messing with the past. Even if the math hints at weird possibilities, nature seems to have safeguards.
That's a fair summary of the prevailing view. While relativity opens theoretical doors, there's a strong suspicion, backed by the lack of paradoxes in our observed universe, that something fundamental prevents causality violation via backward time travel. Maybe quantum gravity holds the final answer.
It's amazing how these far-out physics ideas have become such common themes in our stories, though.
Oh, completely. Science fiction has been wrestling with these concepts for decades, exploring the what-ifs.
We mentioned Back to the Future and the grandfather paradox. That's probably the most famous example.
Definitely. And Groundhog Day, while maybe not strictly scientific time travel, uses that time loop idea brilliantly for character study.
Looper played heavily with bootstrap ideas, didn't it? The self-fulfilling loops of violence.
It did. And even Avengers.
Yeah.
Endgame tried to tackle it, using their version of branching timelines, sort of a nod to many worlds, even if the mechanics were pure fantasy.
Interstellar stands out for trying to get the relativity part, the time dilation, right? Thanks to Kip Thorne.
Absolutely. A great example of grounding sci-fi in real physics. Then you have films like Predestination, which, as you said, is a pure bootstrap paradox puzzle box.
And Harry Potter. The time turner in Prisoner of Azkaban, they go back, but everything they do just makes sure the past happens exactly as it already did.
Which feels very much like the Novikov principle in action, doesn't it? Fulfilling destiny, not changing it.
Yeah, and Doctor Who has done pretty much everything imaginable with time travel over the decades. Fixed points, alternate timelines.
It's a whole sandbox for these ideas. Fiction really helps us visualize and grapple with what these theories might actually imply if they were real.
So wrapping this all up then, it seems like the big takeaway is future time travel. That's real, predicted by relativity. Speed and gravity mess with time's flow.
Correct. That's established physics, observed and measured. Time dilation is a fact.
But going back in time, that's where things get incredibly speculative.
Very much so. Wormholes, Tipler cylinders, cosmic strings. They're theoretical possibilities within relativity, but they all seem to require impossible conditions, or things like exotic matter, negative energy, infinite structures, stuff we have no evidence for and might be fundamentally impossible.
And quantum mechanics offers ideas like many worlds to maybe solve paradoxes philosophically, but gives us no actual way to travel between timelines or into the past. Entanglement doesn't work for it either.
Exactly. So for now, traveling to the past seems confined to theory and imagination. As Kip Thorne said, it would likely require super advanced technology, maybe based on physics we don't even conceive of yet.
But just thinking about it, exploring these ideas, it really deepens our understanding of time, space, reality itself. It pushes the boundaries.
It absolutely does. It forces us to question our basic assumptions about how the universe works.
So a final thought maybe for you listening. If we ever did find a way to travel to the past, and it was possible, what would that tell us about the universe? How would our understanding of cause and effect have to change if the past wasn't fixed?
That's the truly profound question. What kind of reality would allow its own history to be rewritten? It's definitely something to ponder.